Hi, my name is Junko Yoshida. I'm an independent journalist reporting on various semiconductor technologies as well as automotive. I am here today with two Yole analysts who are experts in power electronics. And the two gentlemen just came back from PCIM. So I would like each analyst to introduce himself. Hi, Hassan. How are you?
Hello, everybody. So my name is Hassan. Thank you, Jinko, for this opportunity. So my name is Hassan. I am a senior power analyst at Yole. I am following this data center market since a while now, and I'm glad to be here today for this grateful interviews.
Hi, Roy. Nice to meet you.
Hi, Junko. Thank you for the introduction. So yeah, also an analyst at Yole Group, currently focusing on the power GaN market and GaN's role in the future data centers.
Excellent. You know, it kind of struck me that PCIM suddenly has become data center conference, it seems. So in a nutshell, Hassan, tell us what was the biggest news at PCIM?
So as you mentioned, everybody is talking about AI, data center infrastructure. There is a new component called the solid state transformer, is one of the biggest breakthrough for AI infrastructure. So what is the solid state transformer? The converter that's convert from the megavolt AC from the grid, that could convert to the famous 800 volt that is has been pushed by NVIDIA also to enable very high power density and high computing density as well at the rack level.
Well, actually, let's step back here. When you talk about SST, why suddenly SST got under the spotlight? Because my understanding is SST technology itself has been talked about since 1960s. So why now?
First of all, we should understand that why 800 volt came for this data center. So why 800 volts? So simply because it's a matter of efficiency and feasibility to make these famous 1 megawatt rack. So we do need 1 megawatt rack. Why? Because NVIDIA and all these AI chips maker are going to install all their GPUs inside the same rack to gain in latency and to shorten the distance between different GPUs. Like we will have 72, for example, GPUs working at the same time, really at the same time together and at the same simultaneously. So we do need this such high power to coexist in the same place.
Yeah.
Instead of putting several racks to do this 1 megawatt rack, we do need this 800 volt. Why? Because if you divide the power divided by voltage with that conventional 50 volt DC bus, you will get 20,000 amps in the DC bus bar if you divide 1 megawatt by 50 volt. So that's for sure unfeasible. It's physically impossible to have this 20,000 amps in a DC bus bar. Copper will be, I don't know how much tons. So that's why we do need this 800 volts. So when we divide the 1 megawatt power by 800 volt, we will reach 1,250 amps. So this is the reason why we do need 800 volt DC bus distribution.
Yeah.
And so from this point, we started to think how we create this 800 volt. The first idea was, okay, we will do a conversion from the grid distribution to the low voltage AC grid. It means 230 volt AC. Mm-hmm. And we will create 800 volt DC bus bar. But rapidly we realized, okay, why we are doing that for each rack, and that will cost us more conversions losses.
Oh, yeah.
And we realize, okay, why don't we do it? Don't we do it at the facility level, at the bigger scale,
Oh,
from the beginning, before getting to low voltage AC? Let's convert the megavolt, like the 15 kilovolt coming from the grid, to
yeah.
have a 800 volt DC distribution to all the racks. And this is
Ah,
why SST now becomes a must-have in such a new AI facilities to, at the same time, distribute 800 volt and gain in the efficiency wise. Because if we do it for like locally for each rack, we will pay a lot of losses, and it's close to the GPUs as well. So that's what we are also trying to avoid.
now, so SST suddenly come into spotlight, but at the same time, SST has not been used at the facility level, as you'd explained. So tell me that what exactly SST, if we decide to embrace SST, what power electronics components or what other system that we use today will be replaced by SST?
What we will replace for sure is so first the passive and conventional low frequency transformer, the bulky transformer we used to have and at the facility level for data centers, hospitals, all the big
Right,
industries.
yes.
And then the power supply unit we used to have in data center in the racks. So that stage also will be replaced by this SST. Another thing is the AC UPS, because AC UPS also used to be in cascade in the chain.
Mhm.
And now if we have a DC bus created just after the SST, we will have to readapt this AC UPS to be a DC UPS this time. So
I
three
see.
major changes actually happening at the same time.
All right. If that is the case, let's focus on the power electronics components such as
Yeah.
SiC and
Yeah.
GaN. Tell us that what impact the adoption of SST has on those components.
So as we said, so one of the driver to adopt and embrace SST is the efficiency. And definitely we have mature high voltage IGBT existing in the market, but what everybody is talking about now is silicon carbide power modules. Why? For two things: to be able to switch at higher frequency, so gaining in density, and saving also losses at the facility level, because 1 or 2% saving is a big amount of money for hyperscalers if we look on the annual electricity bill. So that's why SST is, I would say, silicon carbide territory, dominated by silicon carbide. 3.3 kilovolt and 2 kilovolt, and of course 1200 volt for the secondary side. That's how I see currently the market, and all players are, and even IDMs and SST makers are announcing this their roadmap around the high voltage silicon carbide power modules.
So it's a big opportunity for SiC.
Yes.
However, I want to talk to Roy because what's the impact on GaN?
Yeah, so definitely. So for the same reasons that Hassan mentioned about silicon carbide, GaN is also allowing high switching frequency, so high power density, and also lower losses. But this time, GaN will be used in the intermediate bus converter, receiving the 800 volts and converting it to 48 volts. So this is what we're going to see in the future generation, and we see a lot of opportunity for GaN there because of these advantages that GaN is bringing. Also, GaN has no competitor there, so silicon is less performant there. So this is a sweet spot for GaN. This is why all industrial players are pushing to use GaN in this stage.
All right. So the difference here, what I can discern, is that the SSD provides a lot of potential for SiC players, while GaN players already are seeing the fruits of the opportunity because the whole industry or the whole data centers haven't moved to SST yet. Is that correct?
So yes, definitely. I mean, SST will come maybe later this decade, so it's a later generation, let's say. But today, I mean, in this conventional generation, we already see GaN in the stage from 48 volts to 12 volts. So this is also a DC conversion stage, and GaN is performing a lot better there and allowing increased efficiency. And even a 1% increase in efficiency could save a lot in electricity bills. So yeah, even today, before the future generations, we already see a huge adoption of GaN in data centers.
All right, I think this would be a good time to talk about, we were discussing before this recording, Hassan told me, well, 800 voltage, that's the ultimate solution. But in fact, we're not there yet. And Roy, you told me that there are, like, it's not a single line, but there are many stages of the transition, the phases people are talking about. Let's talk about different transitions that the industry is plotting right now.
So yeah, as we said, so for me, the SST is the ultimate solution. Maybe 800 volt, maybe one comment is because we started also to hear about 1500 volt, so plus minus 800 volt.
Oh my goodness.
As a real ultimate solution, and we never know because we are getting higher and higher voltage level in all cases. But before getting this 800 volt at the facility level, we should start by 800 volt at the rack level, which is what I call also the sidecar rack that will create locally from the 230 volt AC, the 800 volt DC for the high computing density racks.
Yeah.
So this is what we are seeing for end of this year, early next year, sidecar rack. We have seen some products in the OCP by some players, but they are still working on to create the sidecar and provide the sidecar as soon as possible. And once we get this maturity for this 800 volt, because behind this power supply unit, you have a lot of the whole ecosystem around the 800 volt, like fuses, protection sensors, power distribution unit, and so on. So this is also an exercise to see the full picture about 800 volt, starting from small 800 volts units, let's say, before getting for the higher power. And once it's established somehow for the rack level, we will make a higher power sidecar that could distribute for several racks. And as we said, the ultimate solution would be to create the 800 volts for the whole facilities.
So it's a kind of isolated solution that you can minimize the risk, but at the same time, you can learn as you testing. Interesting. Yes. From the GaN's point of view, how GaN's demand would increase by the introduction of sidecar solution?
I would say, I mean, for the sidecar solution, based on industry feedback, we see silicon carbide more there at this stage. But then we will be in the 800 volt architecture, so we would need to add the high voltage IBC. So this is where we will GaN penetrate actually. So not in the sidecar rack, but just after it, receiving the 800 volts and converting it to 48 volts. So this will come in the next generation, and this is where GaN's sweet spot is really is.
All right. So tell me a little bit about timeline then. You actually throw in the wild card 1500 voltage, but it's like, let's stick the 800 for now. Yeah. And what's the timeline you see, and what needs to happen between now and then?
Again, for the sidecar rack is something we are very close to it, because the next generation ribbon Ultra is going to be on 800 volt. That's for sure. So ribbon Ultra is getting out in the next year. So 800 volt is under development for the next year, or let's say under validation. Then we will see more and more sidecar at higher scale and higher power, maybe in 2028, 2029. Until we see this, again, as I said, this experience with the 800 volt distribution between different racks. And in the meanwhile, I do believe that there will be some SST project for sure, like a pilot project, to get more experience from the field about this distribution, DC distribution. And for us, the SST will have the ramp up between 2029 and 2030 to have this before getting the mass production.
The system there seems to be some anxiety that whether it's going to be it's going to work. Technically speaking, what has not been tested yet? Why people are a little bit anxious about, before jumping, right onto everything to SST. What is holding people back?
Yeah, there is a lot of, I would say, technical details about that. Yeah. One of them is that transient response. What does it mean? Because GPUs have a peak transient response, like when they run at full load, and they could exceed the normal and nominal power. This is one of the things, and here we should actually size the SST correctly that absorb this transient response somehow, and do not make what we call the flicker on the whole grid distributed. Yeah. So this is one of the things. We have also the mean time between failures for all the components we are adding, because that didn't exist before. All the protections, sensors, even semiconductors, working at this profile load with such a high voltage, like the DVDT, the EMI issues, a lot of things, and bunch of details. We didn't have a real feedback and experience before. So that's why people are, as you said, reluctant before embracing this SST technology.
Interesting. So idea is there and people working on it, but it still needs to be validated. That's sure. Interesting. All right. So my last question to Roy, that when we talk about the GaNs market, it seems like there's it's one thing to talk about ultimately what it's going to look like, but there's an immediate market that people can take advantage of. Can you tell me that the market projection, or that what needs to happen in the GaN world in terms of the improvements?
Yes, of course. So if we talk about the GaN market, we're talking about fast chargers. I mean, this was the first enabler for GaN, and this is where we still see a lot of volumes for GaN devices today, and they will remain the dominant revenue contributor, let's say, up to 2030. However, other segments will take some share in this market as well. Like one of them is data centers. We talked about IBC, high voltage IBC, and also we see some other segments growing as well, like the energy segment. We're talking about GaN in microinverters, for example, or humanoid robots will come a bit later this decade as well. So as the humanoid robots units or volume is growing, the GaN market will grow as well, because we can introduce GaN in motor drives and robotic joints, for example. So we're not only talking about data center and the GaN market, a lot of growth or evolution is happening in other segments as well. In terms of improvements, we're talking about new technologies like bidirectional switches, like new substrate, engineered substrate, like new architecture for GaN, vertical GaN. So yeah, a lot of is happening in the GaN markets, and it's not just in data centers, let's say.
Interesting. I'm glad you expanded the conversation. But thank you very much for your time. It was fun. It's always new things happening in the power electronics world. Thank you.
That's it.
Of course, it's been a pleasure.